Hi, in this video we're going to talk about the electronic configuration of group 1 and group 2 metal cations. Today we're going to learn how to predict the charge of a group 1, group 2 metal cation based on its electron configuration, and we're going to see how periodic properties help us understand what's going on at the atomic level as far as our electron configurations are concerned. As a review, let's quickly revisit the electron configuration of neon that we've talked about before. Recall that neon has an electron configuration of helium 2s2 2p6, which means its electrons completely fill the 2s orbital and the 2p orbital if we put our 6 electrons in here. And so what this means is that we have a filled valence electron count. And as we then start to understand that this is the reason why neon is so inert, in that it has no ability or no tendency to react simply because its s and p orbitals are filled. We can rationalize neon's inertness in light of the fact that its s and p orbitals are completely filled with electrons. If we now start talking about sodium, we can compare sodium to neon, and we can see that neon had an electron configuration 2s2 2p6. Well, sodium has all of those electrons too, plus it has this extra electron that then gets added to the 3s orbital. And so its electron configuration is neon plus 3s1. And so we can see that it has this extra electron. We can ionize sodium by removing this extra electron, forming a cation, so forming sodium plus. In other words, if we remove this electron from the orbital, remove it from the 3s, we now have a sodium cation. And you'll notice that we always need to invest energy to do this. So this is a positive 496 kilojoules per mole that we would need to ionize sodium. So the other thing to think about with regard to sodium is, as it says down here, it's always the outermost electrons that are being removed. So if we kind of harken back to the Bohr model and remember this idea of sodium with our 11 protons, and here we have our nucleus here, somewhere close to the nucleus we have 10 electrons that represent the 2s, the 2p, and the 1s shells somewhere in here. And it's this outermost 3s electron that's vulnerable to being removed. It's this outermost electron that can be easily or most easily removed. Let's look now at a table depicting the ionization energy for all of the group 1 metals. If we looked down the group, what do we notice? We start at 520 with lithium, 496 for sodium, and notice the trend is that the ionization energy decreases as we move down the group. Well, why is that? Notice that the energy investment that we have to remove that first electron is less for cesium than for lithium. If we go to the next slide, we start to understand this trend a little bit more. We see that our group 1 metals also increase in size as we go down the group. So what is happening here is that our metals are getting larger as we move down the group, which means that those electrons that we're removing, or that electron that we're removing, is getting further and further away from the nucleus. And in fact, if I chart the ionization energy on the y-axis versus the radius on the x-axis, I can see a correlation between the ionization energy and the size. So in other words, this electron for cesium that I'm removing, okay, is very far away from the nucleus. The electron for lithium that I'm removing is very close to the nucleus, hence the change in ionization energy. Well, if we can remove one electron, then you can be sure that we can try and remove a second electron. And what do we notice as we move from the ionization energy of the first reaction here to what's called the second ionization energy, so first, second, third ionization, etc., etc. The ionization energy is much larger. And this is always the case. It's always true that the ionization energy of the second ionization will be greater than the ionization of the first. And that can be understood in terms of removing a more closely held electron. But notice this change, this humongous change between about 500 kilojoules and about 4,500 kilojoules, okay, that factor of like 9-fold increase is very substantial. Well, why is that so great? Well, let's remember our electron configuration, 2s2, 2p6. The only reason I'm not drawing the 1s is because they really don't factor in here. So here, keep in mind that if I remove one electron, I'm removing this 3s electron right here. So this guy is eliminated after we invest about 496, it said, kilojoules per mole. If I want to remove a second electron from sodium, fine. But I'm going to want to have to come in here and remove this p electron here. That one is much more costly to remove and cost me about 4,500 kilojoules. So much more substantial energy requirement. And we generally see this as we dip into the filled 2p shell. It's harder to remove that electron. On this slide, I'm basically showing that the same trend that we observed for sodium, going from 496 kilojoules to 4,562 kilojoules, is observed as well for the other group 1 metals, lithium, potassium, rubidium, and cesium. So it's always much easier to remove one electron than two, and in the case of group 1 metals, it's a substantial difference. We're going to use this information that we've been talking about to predict that sodium will give up this electron and form a sodium plus ion, which has the same number of electrons as neon and also has a filled 2s2 2p6 configuration, and we say that it is isoelectronic with neon. In other words, if you were just looking at the electron cloud, you would not be able to tell the difference between sodium and neon. They would have the same configuration, same number of electrons in the same orbitals. Because all of the group 1 metals have similar electron configurations, it's not hard to predict that they're going to have similar they're going to form similar ions. So lithium has an electron configuration of helium 2s1. Sodium, we've already said, has an electron configuration of neon 3s1. Potassium is argon plus a 4s1. And then we go down to rubidium. We're going to have krypton 5s1. And hopefully you're getting the picture here. Cesium, we're going to have xenon 6s1. Well, this outermost electron is going to be the one that's most easily removed. So for lithium, we're going to remove one electron, and we're going to form lithium plus that has an electron configuration that's just helium, isoelectronic with helium. For sodium, we've already said sodium plus, isoelectronic with neon. For potassium, we're going to readily form a potassium plus ion and become isoelectronic with argon. Rubidium, same thing. All of these group 1 metals becoming isoelectronic with the noble gas that would lie to their left in the periodic table, if you were to lift the periodic table out in some kind of string or something in a list. Alright, so all of these outermost electrons, 6s electrons, are removed. And remember, as we go down the group, it's easier to remove the 6s electron than it is to remove the 2s or the 3s. So this is another depiction of why that 3s electron that we talked about for sodium, why it's harder to remove that one than the 6s. So the ionization energy here, as we move down the group, the ionization energy decreases, becomes easier to remove the electron. Okay. Let's look now at our group 2 metals. What's going on with the group 2 metals? Well, we see that we remove an electron from beryllium, magnesium, calcium, and I've listed those ionization energies in the table. And it turns out that we observe the same trend. So 900 kilojoules to remove an electron from beryllium, and the trend is that the ionization energy decreases as we move down. And the second ionization energy, remember we saw this seismic jump for the group 1 metals, so this huge jump. We also see an increase when we go, say, from magnesium at about 750 kilojoules to 1450 kilojoules, so about twice as we go here to here. But notice it's not as huge of an increase as we saw with sodium. Well, there's a reason for that. It goes back to the electronic structure that we'll talk about in a minute. We don't see a jump for our group 2 metals until we go to the third ionization. So with the third ionization, this is where we really start to see an enormous jump in terms of the energy investment to remove a third electron. Okay, so for magnesium, removing 1 electron, 750 kilojoules per mole. 2 is about 1400. And then we want to go up to 3 electrons, want to remove a third electron. Now you're talking 8,000 or so kilojoules per mole, a huge energy expenditure. Okay, listed another way or represented another way is on this graph. Here I have the ionization energy on the y-axis versus the first, second, third ionizations. And you'll see for all of these group 2 metals, removing 1 or 2 electrons, not too bad energetically, but then removing that third electron, here's where you saw these really high ionization energies for these group 2 metals. Take all of this together and we see that magnesium, we can readily think of it. We can think of magnesium losing this 3s2 electrons and becoming again isoelectronic with neon. Well, if it lost those 2 electrons, then we must form magnesium 2 plus. Okay, would be isoelectronic again with neon. If we were to lose any more electrons and try to form, say, for instance, a magnesium 3 plus, well, we've already lost the outermost electrons. Now we'd have to dip into our filled shell and start getting into the 2p. And as we've talked about, that becomes restrictive. That's very costly energetically. And this is the reason why we saw this meteoric rise here for magnesium. Removing that third electron is a lot more costly than removing the second. So we're going to predict that beryllium, which has an electron configuration of helium 2s2, will lose these 2s electrons and become isoelectronic, beryllium 2 plus isoelectronic with helium. The same thing's going to happen for our other group 2 metals. I'll just show you one more here. Calcium has an electron configuration in its metallic state with argon 4s2, and now as we form a cation, we're going to lose these 2 electrons here, so that calcium 2 plus is going to be isoelectronic with argon. And again, removing any more electrons than that just doesn't make sense. Alright, well, I want to thank you for watching my video and hope you have a good day.